uh, it is it is considered as a non-hydrocarbon, and the group or the family of this compound with these types of functional group is called carboxylic acids. It's called carboxylic acid, or in the other way we also call it alkanoic acids. So that is non-hydrocarbon. And another examples, we have something like imine, because if you look at it here, apart from carbon and hydrogen, there is also nitrogen. And we also have thiol group, something like CH3SH. So it means that apart from carbon and hydrogen, we contain sulfur. So this is for the non-hydrocarbon. So as I said, in organic chemistry, we have hydrocarbon and non-hydrocarbon. So now we are going to look at the classification of this non-hydrocarbon. So in the case, although I think we talked about this in our previous video, and let's briefly also talk about it here. So we said under this non-hydrocarbon is actually classified into two, which is aliphatic and aromatic. So hydrocarbon is classified into aliphatic and aromatic. And of course, the aliphatic is divided also into two, into straight chain and the cyclic compound. So when you say straight chain, it means that there are compounds that the compound are in open chain. They are straight, something like this. They are straight. When you say they are straight, it means that they are open. All the carbon are in straight. They are all in straight. So that is why they are called straight chain. And then we also have, apart from this, we also have cyclic. And when we say cyclic, it means that there are those compounds that are in cyclic form. They are in cyclic form, something like this. They are in closed chain. This is cyclopentane. Sorry, this is cyclohexane. 1, 2, 3, 4, 5, 6. So this is cyclohexane. You can have something like cyclopropane. 3 carbon. So this is cyclic. And then that is for the cyclic compound. So aliphatic is divided into straight chain and cyclic. And then after this, we also have under aromatic, we have cyclic. So all aromatic compounds are cyclic. And then for the straight chain is divided into two, that is saturated and unsaturated. When we said compound is saturated, it means that all the carbon to carbon in the case of this saturated, all carbon to carbon is single bond. Between each and every carbon is single bond. So the carbon to carbon in a saturated hydrocarbon, they all have straight chain. They all have carbon to carbon single bond. So in between each and every carbon in saturated hydrocarbon, they have single bond. But in the case of unsaturated hydrocarbon, so that is why under saturated hydrocarbon we have alkanes. So alkanes is a family of compounds that have carbon to carbon single bonds throughout, and it has a general formula of CnH2n plus 2. And we talk about how some family of alkanes are obtained from this formula from our previous class. And then the next thing after saturated hydrocarbon is so the general member of this saturated hydrocarbon is alkane. So alkanes, they are saturated hydrocarbon. And then the next thing that we also going to talk about under this is under unsaturated hydrocarbon. So we have alkenes. So in alkenes, okay, apart from alkenes, we also have alkynes. So in alkenes, between carbon to carbon, at least in the compound or in the family of alkanes, you'll find at least between carbon to carbon to have not less than at least 1 or 2 double bonds. So you see that between carbon to carbon there is a double bond, and in the case of alkynes, between carbon to carbon there is triple bond. So they usually have triple bond. That is in the case of alkynes. So alkenes and alkynes are unsaturated hydrocarbon. And why are they unsaturated hydrocarbon? Is because they have at least at least one or two double bond or triple bond in their compound, and that is in the case of unsaturated hydrocarbon. So I think I actually discussed on this last week. I discussed on this. So we are now we talk about the family of alkanes. We talk about homologous series. So this time around, we are going to look at what you call hybridization. Hybridization will be the next topic that we are going to look at. But before we talk about the hybridization, these are the general formula of alkanes, and we have cycloalkanes. So we are going to look at some family of these alkanes. But before that, we have classification of carbon. Classification of carbon, we have primary carbon, we have secondary carbon, and tertiary carbon. So how primary carbon differ from tertiary carbon? So in the case of primary carbon, you will see that it has only one carbon. It's only one carbon that is directly bind to it. Like for example, in this case, this is a typical example of primary carbon here. This is an example of primary carbon. So if you actually going to open up this structure, you will see that we are going to have a carbon like this, a carbon like this that is directly binded to this carbon, and then we have hydrogen here. We have free hydrogen. We also have another free hydrogen here, then another free hydrogen. So if you can look at this, you will see that this carbon here is directly binded to only one carbon. So that is why it's called primary carbon. And then if you look at this carbon, you'll see that it is directly binded to this carbon and this carbon. So that is why it is secondary. And then for the tertiary carbon, you will see that this carbon here is directly binded to three different carbon, and that is why it is called tertiary carbon. So, and then the next thing that we are going to look at under this is so hydrogen also can be in the form of primary, secondary, or tertiary according to the type of carbon they are bonded to. So now the next thing that we are going to look at is hybridization. So what is hybridization? First, we have to understand that from our basic knowledge of chemistry, we have what you call orbital. And these orbitals, we have s orbital, we have what you call s orbital, we have p orbital, we also have d orbital and f orbital. So these are what you call orbitals, and each of these orbitals have their shape. They have their shape. So generally, s orbital, it is spherical in shape. S is spherical in shape. It is spherical in shape. And then we have p orbital. So s orbital is spherical in shape. And then we have p orbital. So spherical is something like appears in cycle, and then we have p orbital. So p orbital is dumbbell. It has dumbbell shape. So, and this p orbital is divided into three. So this dumbbell, when we say something is dumbbell, this is dumbbell. This structure you are seeing here is dumbbell. This is dumbbell. Or I can actually draw it again. So this is something like this. This is dumbbell. This is dumbbell. This is what we call a dumbbell shape. But of course, this p orbital is divided into three. We have what you call p, we have px, we have py, and then we have pz. We have px, we have px, we have py, and then we have pz. So s orbital is made of p orbital is made of three different p. So we have px, we have py, and we have pz. So remember, even from the basic mathematics, if you have the p in the horizontal direction, so is px, so this is px. And when it is actually vertical, something like this, it is py. Now when the shape is now look like this, we call it py. So this, sorry, we call it pz. Pz. So we have px, py, and pz for dumbbell. So what is hybridization? Hybridization is a combination of two or more orbitals. So when you have two or more orbitals combined together, they will produce what we call hybrid orbitals. And these hybrid orbitals have their properties that is differ from individual orbitals. Like for example, s orbital is spherical, p orbital is dumbbell. But if you have sp3, the structure is neither spherical, neither dumbbell. So that is what you call hybridization. It's a combination of two or more orbitals. So when you have two or more orbitals combined together, they will produce what you call a hybrid orbitals. And these hybrid orbitals have properties that is unique and differ from the individual orbitals that form them. Okay, so now we are going to look at the different types of orbitals and how these different orbitals are being produced. So that is the next thing that we are going to look at. Okay, so let me actually talk about these types of orbital here. Okay, so now we are going to look at the different types of orbital. And these different types of orbitals, we are going to start with carbon. So carbon, remember the atomic number of carbon. The atomic number of carbon is 6. And of course, if we are going to write the electronic configuration of carbon, it's going to be 1s2, 2s2, 2s2, and then 2p2. Because we can clearly see that the atomic number of carbon is 6. Atomic number of carbon is 6. So this is the atomic number of carbon is 6. So we are going to start with 1s2, 2s2, then 2p6. So we are going to do what you call a box configuration. So here we have 2 electrons here, and then also here we are going to have another 2 electrons, 1, 2. And then of course for the 2p, we have, remember we said for the 2p we have px, we have py, and then we have pz. So therefore we are going to have 3 boxes. So in the first box we have 1 electron, and in the second box we have 1 electron. So it means that carbon, this is a carbon, this carbon is at the ground state. We call it ground state. We call it ground state. So the carbon is at ground state. So now, if we look at this carbon at the ground state, there is only 2 unpaired electrons. There are only 2 unpaired electrons. So if we have 2 unpaired electrons, what will happen? Since we have only 2 unpaired electrons, it means that this carbon will only bind to only 2 atoms, 2 hydrogen atoms. So therefore, at the end, if this carbon react with hydrogen, then we are going to have something like CH2. But this CH2 is highly reactive. It is highly reactive. So since it is highly reactive, and usually it is very hard to see it in a free state. So as a result of that, we usually use the carbon that is in the excited state. And how are we going to have a carbon at the excited state? First, we are going to look at what are the orbitals in that carbon that have the same energy level. Of course, we have 2s2 and we have 2p2. So because this one have 2 and this one have 2, it means that they have the same energy level. So since they have the same energy level, it means that electrons from 2s can be transferred to 2p because they are of equal energy level. So if that happened, if something like that happened, then what are we going to do? Then it's the same carbon with 6 atomic number, but at the end we'll have something like 1s2, 2s2, 2p6, 2p2, 2p2. So 1 electrons from here will be transferred to this 2p. Then therefore it means that at this stage we are going to have 2s1, then we have 2p3. So it means that in this case we have only 1 electron here, and then we have 1 electrons in each of these boxes. So it means that at this point in the excited state, we have 4 unpaired electrons. So since we have 4 unpaired electrons, what will happen? Since we have 4 unpaired electrons, it means that the carbon at the excited state, we call this one carbon at the excited states. So it means that it has 4 unpaired electrons. It means that it can actually form 4 covalent bonding with hydrogen atoms. So that is why at the end we are going to have something like CH4, which is methane, if you can remember from our previous classes. So now, if we have this, what will happen? How do we get hybridization? Of course, we have 1s here, and then we have 3p because we have 1 electrons here, 1p here, 1p. So therefore, at the end, the hybridization here is going to be something like this. sp3, or we can say 4sp3. Why is it that it is 4sp3? It's because we have 3p and then we have 1s, so making 4s. So we have 1s and then we have you have 3p. Px, Py, and Pz are all involved in the formation of this. And we also have another way of getting this hybridization. Let me follow the other way. Now, we have, let's say we have methane, CH3, and we want to know the hybridization of this methane. How do we know the hybridization of this compound? It's simple. First, draw the structure of this methane. So we are going to have something like this. So first we have carbon. So we count how many atoms that are directly attached to this carbon. There are 4 atoms. There are 4 atoms of hydrogen. So we have 4 atoms. We have 4 atoms of hydrogen that attach to the carbon directly. And then now we check whether this carbon have any lone pair of electrons. Whether carbon is having any lone pair of electrons. But strictly speaking, carbon doesn't have any lone pair of electrons, because if we have carbon, Let me take it like this. If we have carbon, atomic number 6, so it means that in our first shell we have 1, 2, and in the second shell we have 1, 2, 1, 2. So 1, 2, 3, 4. So there is no any lone pair of electrons. So when we say lone pair, it means that when you have 2 electrons that attach to one each. So but you see that they are all 1, 1, 1, 1 here. So it means that there is no any lone pair of electrons. So therefore we have 0 lone pair of electrons. So since we have 0 lone pair of electrons, what we are going to do, we are now going to say 4 plus 0, we have 4. So since we have 4, it means that there are 4 orbitals. There are 4 orbitals. So since we have 4 orbitals, that means that it's sp3. It's sp3. You have 3p and you have 1s, making sp3 hybridization. And then let's also look another example. Let's look another example. Let's say we have something like ammonia NH3. So first you count how many atoms are directly attached to this ammonia. How many atoms are directly attached to the nitrogen? So it's 3. So we have one hydrogen, another hydrogen here, and then also another hydrogen. And then we have our nitrogen here. So now how many atoms that attach or that are attached to this nitrogen? There are 3 atoms. But is there any lone pair of electrons in nitrogen? Then we now write the electronic configuration of nitrogen 7. So first we have 1, 2, then we also have 1, 2, 3, 4, 5. So it means that we have 7. So in the first we have 2, and on our outermost shell we have 6. But sorry, we have 5. But we have 1 lone pair of electrons here. Then you now say we have 1 lone pair of electrons. So now we are going to say 3 plus 1. We have 4. So it means that our hybridization here is sp3. Since we have 4 here, since it's 4 we have here. So we have sp3 hybridization. Then now state. This is on the ground state. So in the excited state, one electron from this 2s will be transferred to p here. So therefore, at the end, we are going to have 1s2, 2s1, and then 2p3. So that means that here we have only 1 electrons, and here we are going to have 1, 2. So we have 1 lone pair of electrons here, another 1 pair of electrons here, then another 1 pair of electrons here. So now there may be a